an off-lattice Eden growth. So the Eden model is just a model where you have a cluster growing in 2 dimensions. And we're always going to be in 2 dimensions here, but sometimes 1 dimension will be thought of as time. And you have a cluster growing, and the way it grows is that there's a boundary. Well, you can kind of see here the boundary is this pig stuff. So there's some rule of what's called the boundary of the cluster. Here it's just some, things which are a certain distance from the cluster. And then you just add on a point to the cluster chosen uniformly from all the boundary sites. Here sites, there's no sites in this picture. It's actually on R2, on the continuum, but they have some rule about how you add on a little ball within this boundary site. And these kind of rules, I don't even know what the rule is in this. This is a picture from a physics paper, and I didn't really read the rule very carefully, and in fact, it doesn't matter very much, except that because this one is spherically symmetric, you would expect that on a large scale, this thing does look like a ball. If you do it on a lattice, it's known that the thing isn't exactly a ball, but it should be about the same. But the interesting thing is that you now look in some direction, and you think of the pink stuff as like a height function over the substrate. And because it's a ball, it's grown at rate some constant times t, if t is just the time where it's grown that far. But then there are these, and that's not universal. Like if you did it on a lattice, the c would be different and it would depend on your direction. Here it doesn't depend on your direction, but it's some constant you can't even compute, and it's non-universal. But the interesting thing is that the fluctuations on top of that, if you think of this pink stuff as a sort of function, is some universal function living on a scale t to the 1/3 and on a lateral scale of t to the 2/3. And this universal A, which is these fluctuations of the interface, are some special stochastic processes which we want to describe. And what's also supposed to be true is that if you started with a half space, instead of here you just started with a seed in the center, then you would see a half space kind of moving across, or maybe if you started the half space I drew, it would sort of move like this. And you would see another stochastic process at the boundary, which had the same kind of scaling, but it would be a slightly different stochastic process. So the stochastic process remembers the initial data. And that's the kind of thing we want to get at. And these stochastic processes, of course, if you've ever heard anything about KPZ scaling, contain all sorts of interesting things inside them. So for example, in this curve geometry, which is drawn here, the 1-point distributions of this A are supposed to be the Tracy-Whittem GUE distribution. And if you started with flat, the 1-point distributions are supposed to be the Tracy-Whittem GOE distributions. And here with this model, of course, this is all just conjectural. And the conjecture is very broad. So for example, if you had a shag carpet and you looked at the distances an ant would walk in times 1, 2, 3, 4, 5. So you have a random metric, and you look at the balls of radiuses 1, 2, 3, 4, 5, 6, 7. Here they are drawn, and you would expect these things to be approximately balls, but the fluctuations, again, in huge generality, as long as this metric is homogeneous in space, is supposed to look like the same thing. So you would sort of see the same A process, this thing, which is going to be called the Airy process, as the boundary of these balls and random metrics. Now, these models in 2D, where there's no actual direction, seem to be very, very difficult. Nobody's been able to do any of them so far. So we look at directed models, and the most famous directed model is this model of ballistic aggregation. So in ballistic aggregation, you have a discrete height function over a discrete lattice Z. And the way the function grows is as follows. Little blocks are falling from the sky as independent Poisson processes at every site over Z. And the blocks just pile up. If they piled up with nothing more, then the whole thing would be trivial because you just have an independent pile of blocks at every site. But here there's a slight non-triviality that the blocks can also stick to the next tower. So they don't just fall on top of the blocks which are already there, but they also stick to the tower beside, just to the next neighbors on both sides. Okay, so that's called ballistic aggregation. It's like the first model that people were really studying on the computer a lot. On a large scale, it looks like this. So you see this kind of outward growth of the thing, and it's definitely non-trivial. You can see that the thing is not just trivially blocks piling up at each site independently, but it actually kind of looks like an interface and these little trees growing. Now, up to here, everything I've said is completely conjectural. So after this, we'll start to talk about real mathematics. So as a model of this ballistic aggregate, Carter, Parisi, Zhang proposed their famous equation, which we call the KPZ equation. And that's the height function. So this is supposed to be the height function of the ballistic aggregate, is supposed to evolve according to this stochastic partial differential equation, which is basically, in some sense, a heat equation. So here's the dTh equals dx squared h. That's the heat equation. Plus a forcing by space-time white noise. And that's very natural to model the independent Poisson processes raining down on the ballistic aggregate. So that's what's forcing the thing. But then there has to be something to take into account the fact that the growth here isn't just up, but in the lateral direction. And that's this nonlinear term, this dxh squared term, the square of the derivative. Now, why does the square of the derivative model lateral growth? Well, the growth here is out instead of just up. So if you look at the vertical component of the growth, the vertical component is definitely, just from my little tiny picture here, a nonlinear function of the slope. And then you could say, well, in this little picture, the nonlinear function would be something like the square root of 1 plus dxh squared. But what turns out to happen is that it doesn't really matter what nonlinear function you put in there. There's kind of a universality where it just picks out dxh squared as the only nonlinearity which is allowed in the equation. And so this thing is just some model of any nonlinearity, this dxh squared. Okay, so that's how you get the Carter-Parisi-Zhang equation. And if I was better at simulations, I would now show you a computer simulation of the KPZ equation. But I'm not very good at that. But what I am good at is watching the Weather Channel. And it doesn't want to go forward. Let's see. Oh, sorry, just, oh boy, computer problems. Just hold on a sec, I'll have to reopen the thing. Sorry, wow. It's really annoying. Okay. I have to find it now. Oh. Seminário, there we are. Sorry about that. Okay. Can everyone see it now? Is anyone there?
No, not yet. No.
Oh, you don't see it? Okay, so I'm
No,
gonna
we
go
don't see
back.
it. You have to share a screen.
I have to go
again.
back to screen sharing again. Just a second, I have to find it. It's really strange. You know what's weird is that you practice these things and they work fine. And then when you're doing it is the time you have the trouble. It's really weird. Do you see it now?
Yes.
Okay, so sorry about that. I don't know. I have no idea what happened.
Don't worry, don't worry.
It's really baffling. Why does it just not work when you're actually showing other people? Okay, Um, okay, so where were we? We're like here. Okay, okay. Hopefully it'll work this time. So there's this little movie I saw on the Weather Channel of fluff burning in a park in Madrid. Can you guys see this? Is it
Yes.
visible?
Yeah, yeah,
Oh,
sure.
good.
Yes,
Okay, great,
we can
great.
see.
So
We can see the front. Yes.
yeah, so this thing is as much like KPZ as any movie, any simulation you're ever going to see. Um, so you can really see the KPZ front, even with these little. There should be these bubbles because of the Burger's equation, and you really see that with these stochastic things attached to it. Anyway, so I thought that was fun. God knows why it didn't work the first time. Anyway, if you go to the KPZ equation and you translate what I was saying from before, well, you should see this KPZ equation. You should see this, the ballistic aggregate or a KPZ modeling it, growing at rate CT, and then these T to the 1/3 fluctuations on top with these universal process A, which here would be the area 1 process, living on a scale of T to the 2/3. I'd say it's the area 1 process because I started with a flat interface in the simulation of the ballistic aggregate. Okay. So yeah, that's supposed to be the area 1 process. Now, that's equivalent to just saying, well, what I should really do is do a rescaling. So zoom this whole thing out to see very, very large space and time scales. And the right time scales here to see the super interesting stuff is the 1, 2, 3 scaling. So the 1, 2, 3 is because the height here is being scaled by epsilon 1/2. That's the 1. Space is being scaled by epsilon -1, that's the 2, and then time, epsilon -3/2, that's the 3. So these are the ratios of the powers of height, space, time. And if you do that, so that zooms out, that says the height fluctuations at time t are about T to the 1/3. It's exactly the same thing. It's just saying it in terms of this epsilon zooming. So epsilon is the ratio of the microscale to the macro scale here. And as you zoom out, of course, what happens because this thing's growing at rate CT is the thing just goes racing off the picture. So you have to kind of drag it back down by subtracting a huge constant, C epsilon t. So C epsilon t is about epsilon to the -1 times t with some constant. And then you should see some universal stuff, okay? And so all the scalings in the whole KPZ universality picture could be rephrased like this. There's some height function, and under this rescaling, something goes to a Tracy-Whittem GUE or a GOE. So the 1-point distributions in this picture under this rescaling should go to a rescaled by T Tracy-Whittem GOE distribution. Okay. Now, as you do that, the KPZ equation itself gets rescaled. So you can just think, well, how did the H get rescaled under this rescaling? And what happens is that the nonlinear part just rescales perfectly. And you end up with an epsilon in front of the diffusivity and in front of the noise. And so they appear to be just going away. And so you're left with a equation dTH equals dxh squared. And that's just the integral of the Burger's equation, or what's called the Hopf equation. And in school, we're all taught that the solutions of that, as epsilon goes to 0, are supposed to be entropy solutions. And so you might guess that as epsilon goes to 0, you just get the entropy solution of the Hopf equation, but you don't. And that's because the noise is being rescaled perfectly to produce something non-trivial as you go to 0. In fact, if you take the KPZ equation, Brownian motions are invariant. So if you started with a two-sided Brownian motion, and then you waited till time t, you would see another two-sided Brownian motion sort of shifted up. Of course, it's not the same Brownian motion. It says very non-trivial relation to the original Brownian motion, but it's still a Brownian motion. And you can check that if you start the entropy solution of the Hopf equation with a Brownian motion, you don't get a Brownian motion. You get some sort of convex envelope of the Brownian motion. So you're getting some sort of very non-trivial limit. And just how non-trivial? Well, here's the amazing fact. Let's take the 1-point distributions. So this is F, FTR, and I'm sorry, there's a typo. There should be an X in there. So it should say FTXR is the limit as epsilon goes to 0 of the 1-point distributions of this thing. And it doesn't matter what you start with. So I could start with any deterministic initial profile for the H. And then the second log derivative of this asymptotic 1-point distribution functions, FTXR, turns out to satisfy this famous integrable equation from integral PDE, which is the Karamsev-Petyashvili equation, which is written here. And I mean, if you don't know what KP is, well, this is it. You can see that the thing inside of the DR, so if the thing didn't depend on X, say you were starting with a flat initial condition, then nothing does depend on X. The 1-point distributions are just the same everywhere because you started like that. Then you would just get the Korteweg-de Vries equation. Okay, so that's a kind of surprising fact. And the Tracy-Whittem distributions, which many of you may have heard arise in these models, are simply special solutions of the Karamsev-Petyashvili equation. So the GOE Tracy-Whittem distribution, which we write as e to the minus some integrations of a thing called q squared, and the GOA Tracy-Whittem distribution. So these are the limiting rescaled top eigenvalues of the Gaussian unitary ensemble matrix, or the Gaussian orthogonal ensemble matrix, have these special supposed universal distributions. So the GOE has a kind of funny formula where you take the square root of the GOE and then you multiply it by e to the right. So everything depends on this funny function Q, which is the a special function, which is the what's called the Hastings-MacLeod solution of Painlevé 2. Painlevé 2 is written just a little bit below. It's just the name of the special integrable differential equation, Q double prime equals RQ plus 2Q cubed. So you take this funny function Q and you do this stuff to it and you get the GUE and GOE Tracy-Whittem distribution. But now if you take KP and you just look for the natural scaling solutions for starting with what's called a narrow wedge, which would correspond to this curve geometry, or flat, which corresponds to starting with everything h equals 0, then you can guess from the scalings which I told you that the functions should have these scaling structures. You plug those into KP, you get ODEs, and those ODEs just quickly reduce to the Painlevé 2 equation. So that's where they come from. They're just the Tracy-Whittem distributions are just things, special cases of this fact that this thing satisfies KP. Okay, so now I want to try to explain the integrability of the TASEP and how these things are derived. So they're derived from algebra. We don't yet have a physical picture of why these things are true. Okay, so here we go with the TASEP, and TASEP I think most of you have seen, but let me just go through it for completeness sake. So here's the state space of TASEP. Now our TASEP is a little bit special. It has a rightmost particle called x1. So there's no particles to the right of x1. So the state can either be described in terms of particles on Z or in terms of a height function. Let me start with the particles. So the particles, there's at most one particle per site. And so that's the configuration. And as I said, the only thing here is that there's a rightmost one. The height function representation is just to have a height function which only goes up or down as you go from lattice site to lattice site. So it's actually just a function over the lattice. And it makes a step up whenever there's a particle, and it makes a step down whenever there's no particle. And so that's the height function representation. And then the map from particles to height functions is only complete if you decide what the height function is at some single point. But I won't mention that. I mean, you could just decide that it times 0, h at position 0 was 0 or something like that. Okay, so that's the state space, either the height functions or the particles. And now as it goes, what happens is the particle's attempt jumps to the right at rate 1, and they're only allowed to jump if there's nobody in the way. And completely equivalently, a little local max turns into a little local min of the height function at rate 1. So that's happening at every site independently. And so let's watch the thing go. The particle jumps and the height function jumps. And well, that's it. That's TASEP. Okay, so the only twist here is that there's a rightmost particle, and that's the whole model. Now, I'm going to claim that TASEP is actually a discretization of the KPZ equation, which is far from clear when you stare at the thing. But if you look at the rate of the height function jumping down, it basically jumps down 2 whenever there's a little local max. So the rate of jumping down is -2 times the indicator function of little local max. And because this height function is a discrete type of thing, which only jumps up or down by 1, one can do a little calculation and check that that function, so this is just a equality of h's, where h's are our nearest neighbor simple random walk paths. So it's actually equal to 1/2 times the discrete backwards difference operator, so h of x minus h of x minus 1 times the forward difference operator, h of x plus 1 minus h of x minus 1 plus the discrete Laplacian of h. So all the KPZ terms are here. And if you wrote an equation for TASEP, it would just be d of h is equal to this function plus some martingales, which were approximating space-time white noise. And the -1 is interesting because the -1 is actually this minus constant t, which you have to subtract in the KPZ equation. And of course, when Martin makes sense of the KPZ equation, he has to subtract basically an infinity, because at that level, this 1 has become infinity. Okay, so that's the TASEP. And if you look at it on a large scale, it's about the same. But here it is. And we're interested in the blue thing, which looks like a parabola with some noise on top, and that's this area 2 process, the difference. Okay, now there's another thing one can do, which is one can take a TASEP and have it not just taking little local maxes to little local mins, but also going the other way, taking little local mins to little local maxes. And maybe you could have one go at rate p and one go at rate q. If p is equal to q, then you have what's called the symmetric simple exclusion process, and the thing just fluctuates up and down. But maybe you want to take a p slightly not equal to q, and if you wanted to scale these exclusion processes to the KPZ equation, what you should do is you should take the p and q, and so you have a rate of jumping up and a rate of jumping down, and you should let that p minus q be small. So okay, sorry, there's a minor typo in this in this thing, that this p minus q is not in front of everything. It should just be in front of the nonlinear term here. So if you want to scale the KPZ, what you actually want to do, because all these terms scale differently, is you should take this p minus q to be very, very small, and then rescale under a diffusive scaling. So here's the scaling, and it's called weakly asymmetric scaling. Okay, the thing doesn't want to go forward again. Oh, I see. The problem is that it doesn't like this arrow. Oh, shoot. It's frozen again. Okay. Okay, it's crashed again. Sorry. Okay, the laser pointer kills my thing. So now at least we know what's wrong. Okay, so I just won't use laser pointer. So so the p minus q is only supposed to be in front of the nonlinear term, and if you scale it to be size epsilon 1/2, so that's a weakly asymmetric thing, and then you do a diffusive scaling, then the height function actually converges to the KPZ equation. So to get the KPZ equation, you need the exclusion process to go in both directions, almost symmetrically, but slightly off. And that slight offness produces the nonlinear term in the KPZ equation, as you can see here. Okay, sorry, just one sec. I gotta get this going back to how it's supposed to be. Okay, all right. So, in fact, there's what we've got is this huge universality class of models, and in this universality class, so all our favorite models, TASEP and some weird friends of TASEP called push TASEP and discrete time TASEP and things like that. And there's also the ballistic aggregate. So on the right, I've written models which we dream of, and on the left, I've written some models which we actually can deal with. All these models are supposed to rescale under this 1, 2, 3 KPZ rescaling to a universal fixed point.
Sorry, Jeremy,
KPZ.
in your last slide, you had 1 to 4. You had 1 to 4 scaling.
Yeah, so this is 1, 2, 4 scaling, right? So I'll describe that in a sec. Yeah, okay. So if you look on the picture, you see there's another fixed point. What's this called? Edwards-Wilkinson fixed point, down at the bottom in this pink slab. Okay, so the universe actually has 2 fixed points, and Edwards-Wilkinson fixed point is just the KPZ equation without a nonlinearity. So it's just the physicist's name of the stochastic heat equation. Okay, the linear stochastic heat equation. Now that thing has a 1, 2, 4 scaling, and so there's models like, for example, symmetric simple exclusion, which if you did the 1, 2, 4 scaling, you would just scale to this Edwards-Wilkinson fixed point down at the bottom. Okay, so from symmetric simple exclusion, you would never see the KPZ fixed point. You would just rescale under 1, 2, 4 scaling to this Edwards-Wilkinson fixed point. But if you have some slight asymmetry, then what happens is you tune the asymmetry so that instead you're just slightly off this pink slab. That's why it's written as a slab. Actually, it should really be a codimension subspace. Okay, but if you're slightly off in the pink slab, then you tune your asymmetry as you're going along, so you don't just shoot up to the KPZ fixed point, and actually you join this golden road, the KPZ equation in the middle, somewhere in the middle, as it's mediating between the Edwards-Wilkinson fixed point and the KPZ fixed point. So the KPZ equation is what's called a heteroclinic orbit. It joins 2 fixed points as sort of the coupling constant in the KPZ equation, which is in the middle, this lambda, is sent to infinity. You should get to the KPZ fixed point, and as it's sent to 0, you get to the Edwards-Wilkinson fixed point. Well, that's easy. You just put lambda equals 0, and you're at the Edwards-Wilkinson fixed point. Does that make sense, Claude?
Yes,
did that answer your question?
Yeah. Thanks.
Yeah. Okay. So you see, there's 2 scalings, and the scaling, the 1, 2, 4 scaling, we can kind of do now, because the machineries that Martin Hare and Gubinelli and those people have built up for SPDE actually works in a kind of small region around the Edwards-Wilkinson fixed point. So it works for like KPZ up to finite time. So analytically, we understand those things. And so now if you want to know something converges to the KPZ equation or to Edwards-Wilkinson or stuff like that, you can just do that by using analysis tools. Up above this pink slab, we're sort of in the large time limit of the KPZ equation or any of these models. And there's no analytic machinery that can go that far. So we're reduced to, I don't know, not everyone may like that. We're reduced to algebra. Okay, so and algebra, it definitely is. So here's the algebraic fact that makes everything fly, which is that we can compute the TASEP transition probabilities exactly. Okay, so here's a formula. There's many ways to write this formula. I've written it one way here. So this is a formula for the transition probabilities of the TASEP model that I showed you. And so by transition probabilities, I mean literally you start with any initial condition admissible initial condition for the heights. And the only admissibility condition here is that the height should sort of go down after some point, because there was supposed to be a rightmost particle. But otherwise, it's just completely general initial data. And this thing tells you the probabilities of the height function at time t. Okay? So that's the transition probabilities. Now, what it can't do is it can't tell you what the joint probabilities are for the height function at two different t's. But just like in transition probabilities, the way you get that is, well, in principle, you get it from the Chapman-Kolmogorov equations. Of course, here, the Chapman-Kolmogorov equations don't help you very much. And so two-time formulas aren't apparently around, though there have been some special ones discovered by Kurt Johansson in some very special cases. So as far as we know, the solvability goes this far, that, that we know, starting with any initial data, you can calculate the distribution of the height function at time t. Okay? Which is a lot of information. And so the formula, well, let me try to read the formula and you can ask questions. You should ask questions. So the formula says, if I want to know these probabilities, then what I do is I make a kind of operator out of my initial conditions and my final conditions. And these operators, well, you can think of operators as defined by their kernels. And their kernels have two variables. This determinant is acting on L2 of Z, so the variables are now in Z. And these variables you can just think of as the starting point and ending point of some like probability kernels. And here what they are is they correspond to transition probabilities of geometric random walks, either being asked to stay above the final condition or below the initial condition. So you take those transition probabilities, and they're functions of two variables, which I could call U1 and U2, and you just ask for a geometric random walk to either stay above the final condition or below the initial condition, starting from U1 and going to U2. And that's the two variables in these R's. And so you build these operators R, and then the rest of the formula are kind of straightforward things. There's these things like e to the t over 2 grad minus, which is just the transition probabilities of a Poisson process. And there's this q. Q is nothing but the transition probabilities of a geometric random walk. And then there's this weird thing, q bar. Now, q bar, if you take q to the n, then that's the n step transition probabilities of a geometric random walk. And that's something that the geometric random walk is jumping down. And so, of course, the probabilities to go above, it sort of has to have gone n steps down. And then there's some probabilities down below. And above that's just zeros. Q bar is a bizarre thing. It says, no, I'd rather extend this thing as a polynomial above. And well, okay, that's a thing called Q bar, and it goes into the formula. It's just a funny function, and that's it, and that gives you the formula. So you know, in a sense, TASEP is solved by this, and in a sense, it's a completely integrable Markov process, which is my word for a Markov process whose transition probabilities can be solved by a kind of machinery like this. Okay. Now, where does this crazy formula come from? So this is, of course, not a very obvious formula. It comes from about 20 years earlier, a formula of Günter Schütz, who was able to write down the n particle to n particle transition probabilities for TASEP as an n by n determinant full of contour integrals. It's a formula somewhat reminiscent of the Carlin-McGregor formula. It's an amazing fact that you can solve the n particle to n particle transition probabilities for TASEP, except the only problem with it is that this formula is not very good for taking limits as n goes to infinity. Except in one case, if you have wedge initial data, which for TASEP just means all particles packed into the negative Z and no particles in the positive Z. Then it turns out that this matrix has a Toeplitz structure, and taking large n limits of Toeplitz matrices is a classical problem that Johansen was one of the world experts in, and so he was able to take the large n limit and discover this GUE trace-equilibrium distribution. Now, Sasimoto discovered that by trying to row reduce the formula and use some recursion equations that these contour integrals satisfied, he discovered that it can actually be written as a kind of sign determinantal point process on a space of Guth and Zeitlin patterns. And then there's a machinery called Einhard Meta, which allows you to try to compute the top line of such a thing. And in doing so, they reduced the problem to a certain algebra problem, a biorthogonalization problem for Charlier polynomials, which I won't describe because I don't have enough time in this talk. And we were able, using some guess about the KPZ fixed point and then going back, to actually solve the biorthogonalization problem. And the solution is completely general, so that gives you this general formula. And then once you have the thing, you can actually literally take this formula and plug it into the backwards equation for TASEP and check that it works. And that backwards equation turns out to be well posed, and so you get quite a short proof that that's a formula for the transition probabilities. So after the fact, of course, guessing the formula is not something easy. And then I just want to point out that Metetsky and Remenick have been able to derive similar formulas for a number of versions of discrete time TASEP recently. Okay, now you might ask, okay, this formula is so complicated, what am I ever going to be able to do with it? What can you do with such a complicated exact formula? Well, actually, you can do a lot. In fact, I suspect most problems about TASEP which don't involve 2 times can actually be solved this way, and even some which do depend on 2 times. So I'll just list a couple of things. Well, what you do is you just keep working with the formula and you get used to it. So with Li Cheng Tsai, we were able to solve this famous problem of Jensen and Baradan, the large deviations from the Berger scaling limit of TASEP. The probability to see a non-entropy solution is governed by the Khrushchev entropy production. So that can be done using this. It's not direct, but it is hiding inside this exact formula. One can also look at statistics at shocks in TASEP. So if you start the thing with two different say flat heights, then if they're in the wrong order, and I think I drew this wrong, I think I should draw it like this, then there'll be a shock produced here. And you look at the statistics of shock, turn out you want to follow down the characteristics, and it'll just take the maximum of the 2 things it sees. And so you'll end up getting things like in the picture I just showed you, you will get the GOE distribution squared, for example, or many, many other cases. So this is being studied a lot by Ferrari and Najjar, but you can actually just use the formula to derive all these also. And then the one I want to show you is that in the 1, 2, 3 scaling limit, you'll get an exact formula for the universal fixed point transition probabilities. Okay, so let me show you that now. Now, as you take the 1, 2, 3 scaling limit of the formula I showed you, the formula is actually written in a kind of transparent way to make the limit transparent. Each term in the formula actually converges, or at least in some pairs of them. So here's a pair. I'm not going to show you the whole thing, but here's a couple of pieces of it, the most interesting pieces, actually. So maybe look at the one at the bottom. The one at the bottom is one of these R's. So this is the R for the final condition. Now there's a similar R for the initial condition, just upside down. So you were asking the transition probabilities of a geometric random walk to stay above your final condition, and that just becomes in the limit. Well, what do you expect? It becomes the transition probabilities of a Brownian motion to stay above the final condition you're asking, and there'll be a flipped one for the initial condition. and then perhaps the most important piece is that if you take these generators, sorry, not generators, but semigroups of Poisson processes and multiply them by the transition matrix Q of the geometric random walk. Now here, this transition matrix Q of geometric random walk is to an enormous negative power. And you may question that. But it turns out that the transition matrix of a geometric random walk is easily invertible, and it has this terribly simple inverse. So it's just 1 plus 2 of this grad plus the forward difference operator, f of x plus 1 minus f of x. So if you do this, well, I could just write this schematically as e to this enormous epsilon to the minus 3/2 times this minus grad minus, and then plus a half log of the 1 plus 2 grad plus, which is the q to the minus 1. And then if you expand the log, you just cancellations up to the third order, and you find out that this thing actually is basically a third order derivative. And so this d cubed is super interesting, and it tells us that this is a type of probability where the d squareds of diffusion theory get replaced by d cubes. Okay, so here's the KPZ fixed point formula. So this is the formula for the transition probabilities of the KBZ fixed point. So the KBZ fixed point is a Markov process with these transition probabilities. It's, well, first of all, it's the transition probabilities are completely determined by their finite dimensional distributions, just like the distribution of Brownian motion is completely determined by its finite dimensional distributions. The H will actually always be a continuous function with the same regularity as Brownian motion. And in fact, they all look locally like Brownian motions. The fact that their transition probabilities is beyond not obvious, but it's true. Anyway, they're given by these finite dimensional distributions are given by certain Fredholm determinants. And the important thing is that there's a recipe where if you start with an initial distribution, you produce an operator out of it, which that operator you plug into the Fredholm determinant, and it actually gives you these transition probabilities. So the operator is depending on time, and it depends on these x1 through xm and a1 through am. And I should say that there's two ways to write all these formulas. The TASEP formula I wrote a slightly different way, as a sort of one function less than the other function, and this one I'm writing as the endpoint distributions in what's termed an extended kernel. So now the kernel is acting on an m-fold product of L2. These two ways are equivalent, but I sort of write both of them in the two different models just to show you there's two different ways, and you get a lot of mileage out of going back and forth between these two representations. So anyway, the way that the K depends on T's and X's and A's is a kind of trivial thing. It's you just solve some linear differential equations, which is written here as e to the t over 3 d cubed. So that just means solve the area equation, or e to the x d squared. That means solve the heat equation. If you'll notice, some of these heat equations are being solved backwards in time, but it turns out that if t is not equal to 0, then if you have this e to the t over 3 d cubed, it actually sends you into the domain of the backwards heat equation. So there's actually no problem doing this for backwards or forwards heat equations. And the kernels of these operators, e to the t over 3 d cubed minus x d squared plus a d, are just explicit crazy kernels full of area functions, and they're smooth as can be. So there's no problem doing any of this. So that tells you that what you start with your H0 and you produce this sort of core operator KH0, which is called the Brownian scattering transform of H0. And once you do that, you're up in operator land, and the whole thing just sort of evolves like a straight line. You could think of, and then if you want to get your transition probabilities, you project down from operator land by the Fredholm determinant to get your transition probabilities. So this shows you that this thing is a completely integrable system. And so the only thing is, how do you get this operator KH0? Well, you do it with Brownian hitting probabilities. Before we had Brownian motions not crossing H0. Now we have Brownian motions insisting on crossing H0. That's just from some inclusion exclusion. So to produce the KH0, we take this hit operator, which says, what's the probability for a Brownian motion starting at U1 at minus L to be at U2 at time L and to have crossed my initial function H0, to have entered its hypograph. So hypograph just means all the stuff below the function. And that's a little bit important because H0 equals 0 at 0 and minus infinity everywhere else is a kind of natural function in this world called narrow wedge. So you need to work with upper semi-continuous functions. Upper semi-continuous just means it has a closed hypograph. So all of this is very natural. So you just ask for Brownian motion to hit the closed set, which is the hypograph of your initial data along the way from U1 to U2. Okay, so you take these hit probabilities, and now you kind of refocus into the center by solving the heat equation backwards and pull it out to infinity. And that gives you this operator KH0. You can actually compute it in various cases. So for the narrow wedge one I told you before, the KH0 just turns out to be a projection operator. And for flat, well, you might imagine computing it using the reflection principle. And indeed, KH0 just turns out to be the reflection operator. So these are actually operators which you can really compute about your initial data. And from H0 into KH0 is a beautiful continuous, it says injection, bijection, but it's actually an injection of upper semi-continuous functions into the trace class, and therefore you can take the Fresnel determinant and everything's fine. So this gives you a Markov process where you can check its failure because these Ks are continuous in the trace class in the initial data. And it's 1, 2, 3 invariant, as you can check just from the formulas. It's not unlike TASEP. It's not defined for any initial data. The initial data has to be bounded above by something. In fact, it has to be bounded above by parabolas, and then it explodes in finite time. But it's easier just to bound it above by things which are growing linearly. Brownian motion is invariant, and it is the conjectural limit of all models under 1, 2, 3 scaling in the universality class. And let me just finish, because I'm out of time, with the connection to these integrable partial differential equations. And that's because if you have a determinant of I minus k, where k's depending smoothly on some parameter like txa here, then you're very tempted to differentiate the log of the determinant, because the derivative of the log of the determinant of I minus k is just the trace of I minus k inverse times the derivative of k. And traces are nice things. So if you do that, and well, okay, you have to differentiate many, many times in all these variables, and it's not something simple, but you finally derive this matrix KP equation which tells you what the endpoint distributions of the KPZ fixed point are. And the 1 point distribution, the 1 point case is a little bit simpler, and you just get this scalar KP equation. Okay, so all of this is just to show that this KPZ fixed point is a completely integrable system, and I'll just leave you with the picture and maybe stop there and ask for questions.
Thank you very much. Jeremy, is there any question or comment?
Well, an obvious question is, do you think it's possible to avoid these algebra identities and to have an analytical proof of these results?
So we are, yeah, of course, and it's obvious and a very, very good question. We're working very hard to try to show that, oh, and it's frozen again. Okay, there we go. We're working very hard to try to give analytic proofs of these KP equations. I have not succeeded yet. It's kind of hard to imagine that one would be able to have an analytic proof of the Fredholm determinant formulas, because what would such a thing mean? Do you know what I mean? It's not clear how you could have an analytic proof. And I think one of the reasons that I'm so keen about these PDEs like KP is that they at least open the possibility to have something like a hydrodynamic limit type thing going on. Do you know what I mean?
Mm-hmm.
I should say that this is not a hydrodynamic limit, though. These equations are for the distribution functions. You see, it's a little bit different world. Still, I think that's definitely what I would like to do. Now, whether it's possible, it's far from clear whether it's possible. So no one's ever produced an analytic argument, even for the GUE Tracy-Whittem distribution in random matrices. There's nothing even close. In fact, if you look at all even the Yao and the Tau schools, all they're able to do is compare things to the Gaussian case. But the Gaussian case is just a calculation they can't replicate. Anyway, it's a good question. Maybe.
Okay. But so
good question for the next decade.
Work on that. Good.
Yeah.
Any other question?
Hi, Jeremy. Sorry. Go
Hi,
ahead.
Sundar. How are you?
Hi. Please go ahead. I'm doing okay. Nice talk. I have a question. You mentioned large deviations very early, but it could be for another talk. But you can have the Jensen-Vardan function can compute the cost of non-entropy solutions. How does that? I think you're using corner growth model to do it. Is that right?
No. We can do in your language. No, because you need to be able to start with anything, and compute the cost, right? I mean, you're starting with some general initial data. So these aren't corner growth computations, though they're analogous to the corner growth computation. So to do that, I have to be able to start with some generic, so I have to be able to start with some generic thing and ask what's the probability of some generic thing that looks like that time t later. Okay?
Yeah.
Does that make sense? And show that that's, if that thing corresponds to a non-entropy weak solution, then the asymptotics of this Fredholm determinant give you the Jensen-Vardan rate function. Is that?
I was wondering, just in terms of,
Now, I will say there's one thing that you may be wondering, which is that the Jensen-Vardan rate function is a space-time thing. But what you do actually is you divide up time into a lot of little intervals, and then there's a version of the Jensen-Vardan rate function which is actually simpler, which we discovered from looking at the asymptotics of the Fredholm determinant on a little time interval to see one of these pictures. Okay, so if you look at instead of doing Jensen-Vardan, so you're in full space-time, you just ask what governs the probabilities to see at time t something that came from a non-entropy weak solution, and that actually has a really nice formula. It's just the essentially governed by probabilities for Brownian motions to go do this weird thing. Well, not Brownian motions because it's TASEP for Bernoulli walks.
I see. Okay. Anyway. Well, thanks. Very nice talk. Thanks.
Yeah. Anyway, the Jensen-Vardan rate function is high. This function, this Fredholm determinant, it's containing all sorts of unbelievable information inside of it. It may be hard to eke out in a particular case, but it is genuinely easier to study this thing than to try to do the problem from scratch, as well as we can see, because people failed with the Jensen-Verdun theorem without a formula like this. Anyway.
Thanks, Jeremy.
I hope that answers your question.
Yeah, thanks very much.
Is there any other question? Jeremy, you at the beginning of your talk mentioned some relation with the... sorry, Mauro, you want to ask something?
Please go ahead, I will ask you.
Okay. You were mentioning some relation with the KDV equation.
Yeah.
I couldn't get it.
Right. So let me give you the full general big one. It's at the later slide here. Okay, so you see KDV is just KP if you don't have dependence on X. So the KP equation is written kind of in the middle of this slide, the scalar KP equation.
Mm.
So you see, if the function phi doesn't depend on X, it's just KDV. So you should think of KP as KDV in 2 dimensions. Okay?
Okay.
The two dimensions.
But are you expecting solitons here also?
Yeah, no. So I know it's completely bizarre. So the initial conditions we have, I don't even want to talk about. They're not close to the initial condition that had ever been studied for these equations before. And what happens is with these initial conditions, you don't ever see solitons.
Okay.
What you see is things which look like what you might guess are the second log derivatives of distribution functions, right? So they sort of go like this.
Okay.
And kind of straight flatten out. Yeah.
Okay. Thank you, Jeremy. Mauro, you can talk now.
Yeah, I just want to ask, so what about different types, like say what would be called in this framework bidimensional random field, probably. You're just thinking about using sort of Markov property in T. So once you have the initial data and the marginals at T,
right. So it's a great,
you can iterate.
Yeah, so you can do that. It's not terribly useful because the internal integrations are essentially undoable, impossible with the formula.
Yes, I wanted to ask if there is sort of more, I don't know, general formula involving also different T's.
Right. So that's
more direct.
That's a great question, and the answer is nobody knows. So Kurt Johansson can basically get such a formula if you start with narrow wedge. Okay? And it's completely unknown whether this thing can be generalized to other initial data. So it's not clear a formula exists. And from my picture of this thing being a completely integrable Markov process, it's very mysterious why his formula should exist at all. But his formula does exist. So there's 2 possible scenarios. One is that this thing is way more integrable than we think, and there's formulas like the ones you're talking about. And the other possibility is that there's some crazy coincidence for narrow wedge initial data so that you have multi-time formulas. And we don't know one from the other. The problem is that there's very little rhyme or reason for any of this stuff. There's just what formulas you can get by algebra, right? So all I've said is it's a very good question.
Okay.
So there's a bunch of miracles which don't quite fit into the picture. Another miracle which doesn't fit into the picture is that all of this definitely depends on you starting with deterministic initial data. Well, Markov transition probabilities mean deterministic initial data. And so in principle, if you start with random initial data, there shouldn't be any formula. Yet, for Brownian, for example, Brownian initial data, there is a formula. A complicated formula which looks a bit like these formulas. And why that would happen is sort of anybody's guess.
Okay, thanks.
Another one? Okay, yes, no. So thank you, Jeremy. It was a great talk. Thank you very much.
Okay, it was a pleasure. Nice to see everybody.
Yeah,
Thanks,
thank you.
Jeremy. Very nice
Okay.
talk.
See ya.
Yeah.